The definite integral is the basis for half of the work in calculus and therefore requires a significant amount of attention. When one studies the integral, one also learns about antiderivatives. Hi, my name is Jason Rosenberry, and let's start today's lesson by looking at some properties of definite integrals. Here's some rules for definite integrals. Rule number 1, order of integration. Notice that the definite integral from b to a of f of x dx is equal to the opposite of the definite integral from a to b of the same function with respect to the same variable. Basically what number 1 is saying is if you switch the order of those two, then that creates a negative sign in front of the definite integral. Number 2, the zero property. The definite integral from a to a, from any number to itself, of f of x dx is equal to 0. Number 3, the constant multiple property. The definite integral from a to b of k times f of x dx is equal to the constant k times the definite integral from a to b f of x dx for any k which is a constant. So basically what that rule simply says is if you have a constant, you can pull it right out front and go ahead with your integration. Number 4, sum and difference. The definite integral from a to b of a sum or difference with respect to x is equal to the definite integral of each individual term. So from a to b of f of x plus or minus g of x dx is equal to the antiderivative of f with respect to x from a to b plus or minus, again depending on this symbol, the times the definite integral plus or minus the definite integral from a to b g of x dx. There are 3 more rules. Number 5, additivity. The definite integral from a to b of f of x dx plus the definite integral from b to c of f of x dx is equal to the definite integral from a to c of f of x dx. So again, here we're seeing that if this number b is between a and c, then the following property holds. 6, the max-min inequality. If the maximum value of f and the minimum value of f are the max and min values of f on the closed interval from a to b, then the minimum value of f of b minus a must be less than or equal to the definite integral from a to b of f of x dx, which is then less than or equal to the maximum function value of f evaluated at b minus a. Domination. If f of x is greater than or equal to g of x on every single value from the closed interval or in the closed interval from a to b, that implies that the definite integral from a to b of f of x dx must be greater than or equal to the definite integral from a to b of g of x dx. Also, if f of x is positive or equal to 0 on the interval from a to b, that implies that the definite integral from a to b of f of x dx must also be positive or greater than or equal to 0. Let's try an example. It says here, suppose that the definite integral from 1 to 2 of f of x dx is 5. Find each integral. Number 1, we have the definite integral from 1 to 2 of f of u du. So notice that we're using the same limits of integration from 1 to 2, just like with number 1. And we're told that whatever this variable is, that must match this variable, then that answer is equal to 5. And we have exactly that with number 1. We're going to go from 1 to 2 of f of u evaluated with the same variable u, so that answer is just equal to 5. Number 2, we have the definite integral from 1 to 2 of square root of 3 times f of x dx. So using our constant property, this would be the same thing as the square root of 3 times the definite integral from 1 to 2 of f of x dx. And we're told in the beginning of the problem that this definite integral is equal to 5. So 5 times the square root of 3 is 5 root 3. Number 3, here we have the definite integral from 2 to 1 of f of t dt. Notice that the limits of integration have been reversed. So this, number 3, the answer would equal the opposite of the definite integral from 1 to 2 of f of t dt. And again, we're told in the problem that this definite integral is equal to 5, so the overall answer would be negative 5. Number 4, the definite integral from 1 to 2 of negative f of x dx. Again, we could use our constant rule and think of the constant being negative 1. We can pull this negative sign out in front. So the answer would equal the opposite of the definite integral from 1 to 2 of f of x dx, and this gives us negative 5. We can use definite integrals to find the average value of a function. Let's see how. Definition: average value of a function, or mean value of a function. If f is integrable on the closed interval from a to b, its average, or its mean value on that interval from a to b is found by the following. So the average value of function f is equal to 1 over b minus a times the definite integral from a to b of f of x dx. So let's try this out. Use a calculator that can integrate to find the average value of the function on the interval. At what points in the interval does the function assume its average value? Therefore, we want to use the previous formula, so it would be 1 over b minus a. Well, here's your a value, here's your b value. So this would be 1 over 1 minus 0 times the definite integral from 0 to 1 of negative 3x squared minus 1 dx. So notice what happens to the fraction out to the left side of our definite integral. 1 over 1 minus 0 is just 1. So the average function, the average value of function f for this problem would just be the definite integral from 0 to 1 of negative 3x squared minus 1 dx. So now let's use our graphing calculator and the function integration function of that calculator to evaluate this definite integral. So we choose Math 9, negative 3, variable button squared. So here's function integration. The first argument you give this calculator function is the function that you're integrating, comma, with respect to x, so there we use the variable button again, comma, from the lower limit of integration 0 to the upper limit of integration 1, and we should get negative 2. So the average value of function f is negative 2. Now the follow-up question was at what point or points in the interval 0 to 1 does the function assume its average value? So we just found out that the average value is negative 2. So we want to set the function negative 3x squared minus 1 equal to that average value, which was negative 2. And now we'll solve this equation for x. So let's go ahead and get x squared by itself. So we would have negative 3x squared is equal to negative 1. We'll now divide both sides by negative 3. We get x squared is equal to positive 1/3. Therefore, x is equal to plus or minus the square root of 1/3. Now we have two possible answers. However, the negative root 1 over 3 is not in the interval from 0 to 1. So we only have one solution. We have x is equal to the positive or the principal square root the square root of 1 over 3, which also could be written as x equals 1 over the square root of 3, or could also be written as root 3 over 3. So at 1 over the square root of 3, this function assumes its average value of negative 2. Finding the point at which the function takes on its average value is an example of the mean value theorem for integrals, which states that somewhere over the interval of integration, and in this case was from 0 to 1, there must be a point at which the function takes on its average value. Let's now look at a connection between differential and integral calculus. If capital F is any antiderivative of f, then the definite integral from a to x of f of t dt is equal to the antiderivative of f evaluated at x plus some constant. Now let's set x equals to a in our previous equation, and we get the following. Definite integral from a to a of f of t dt would equal f of a, the antiderivative of f evaluated at a, plus some constant. And this guy right here was property number, I think, 2, the 0 property. Since we're evaluating from a to a of f of t dt, that turns out to be 0. So we have 0 now equals f of a plus c. Therefore, the c value must equal the opposite of capital F of a. We can now put this all together and say that the definite integral from a to x of f of t dt is equal to f of x, the antiderivative of f evaluated at x, minus the antiderivative of f evaluated at a. Let's try some examples. Evaluate the integral using antiderivatives. First problem we have is definite integral from pi to 2 pi of sine x dx. So using our previous property, we now know that we can take the antiderivative of sine x, which is negative cosine x, and we can evaluate it at the upper limit of integration minus the antiderivative evaluated at the lower limit of integration. So this answer would be negative cosine 2 pi minus negative would turn into plus positive the cosine of pi. So to simplify, here we have the opposite of cosine 2 pi. The cosine of 2 pi is 1, so we want the opposite of that of negative 1, plus the cosine of pi, which would be negative 1. So this answer is negative 2. Number 2, we have the definite integral from 1 to 4 of 2x dx. So this would equal the antiderivative of 2x. The antiderivative of 2x would be 2x squared over 2, but the 2's divide out and just gives us x squared. So we want to evaluate x squared from 1 to 4. So we plug in the upper value in first, 4. So this would be equal to 4 squared minus 1 squared. 16 minus 1 is equal to positive 15. And number 3, definite integral from negative 1 to 1 of 1 over 1 plus x squared dx. Again, let's find the antiderivative of 1 over 1 plus x squared. And that would be the inverse tangent function. So we want to evaluate the inverse tangent function, or the arctan function of x, evaluated from negative 1 to 1. So we plug in positive 1 first. The inverse tangent of 1 is pi over 4, minus what we get when we evaluate the inverse tangent of negative 1, which is negative pi over 4. So this becomes a plus positive situation. Pi over 4 minus negative pi over 4 is positive 2 pi over 4, which is pi over 2. So the final answer would be pi over 2. Now it's time for you to try a problem. Evaluate the integral using antiderivatives. You are given the definite integral from 1 to e of 1 over x dx. Pause the video while you work on this problem. When you are finished, restart the video to check your solution. So the antiderivative of 1 over x is the natural log of absolute value of x. So with this problem, to get our final answer, we will take the natural log of e minus the natural log of 1. The natural log of e is 1 minus the natural log of 1 is 0, giving us a final answer of positive 1. Let's combine this procedure with our average value formula. Find the average value of the function on the interval using antiderivatives to compute the integral. We have y equals secant squared x, and we're looking at the closed interval from 0 to pi over 4. So the average value of f will equal 1 over b minus a, in this case pi over 4 minus 0, times the definite integral from 0 to pi over 4 of secant squared x dx. So to simplify our average function of f, average value of f, 1 over pi over 4 minus 0 is the same thing as 4 over pi. Now we're going to multiply that by the definite integral 0 to pi over 4 of secant squared x dx. Well, the antiderivative of secant squared x is tan x. So we're going to have 4 over pi times tangent of x, or for our upper limit of integration was pi over 4, so it's the tangent of pi over 4 minus the tangent of 0. So we end up with 4 over pi times the tangent of pi over 4 is equal to 1 minus the tangent of 0 is 0. So we have, 4 over pi times 1, which is just 4 over pi. Therefore, the average value of this function is equal to 4 over pi. In this lesson, we explored the properties of integrals and the antiderivative. Be sure to work the exercises that your teacher assigns, and we'll see you next time.